Hello everybody and welcome back to my channel. So in today's video we will be talking about asymptotic notation. Now before starting with the video, to all the people who like my videos and they see my videos but they do not subscribe to my channel, so please don't do that and just subscribe to the channel. And if you want me to solve any particular question of yours or if you have any doubts, you can just leave it in the comment section with hashtag #CodeMyQuestion and I'll surely help you with it. Also, if you want short notes on all the content that I upload on my channel, you can follow me on my Instagram handle. Over there I upload short notes which includes key points and codes to every algorithm. So now let's start with asymptotic notations. Now what is asymptotic notation? We know that we measure the time or any other factor of our algorithm in terms of asymptotic notation. Now see, we can measure them in two ways. One is mathematically and second is asymptotically. Now mathematically is that it will also have the proper constant. Like for suppose I can have algorithm working in 11n plus 2 times. So this is a mathematical notation for the time complexity of my algorithm. Now if I write it as order of n, so this is an asymptotic notation, which is we just have our attention on the major factors of the equation and not on the factors which are not that dominant, or if they are constants then we just simply ignore them. So asymptotic notations can be expressed in 5 ways. One is using big O, which is the most commonly used. Second is theta, then omega, little o and little omega. Little o and little omega are not that frequently used than in comparison with big O, theta and omega. Now, if you have seen my previous video, you will see that I have used this big O notation a lot of times over there when we were comparing our algorithm on several measures. So these notations are very helpful when we have to compare our algorithm or we have to tell that how my algorithm is working and what are its advantages and disadvantages in terms of some asymptotic notation or a value. So now over here in this graph, over here we can see that suppose fn and gn are the two functions which represent the way my algorithm is working. So this can the way my algorithm is working. So over here we can see that fn becomes small than c into gn, where c is just a constant after this particular point. So after this particular point, what we can say is that my fn is less than equals to gn. Why am I saying gn equals to? Because at this point it is equals to c dot gn. So when we have an equation like this, so over here we can say that my function fn is equals to big O of my function gn. We simply ignore this constant c, and since it is less than equals to, so we can write it as order of big O of g of n. Now this clearly says that either my function is equal to fn or it works or it is less than c dot gn or gn. So for example, if my fn is n square, so we can write it as big O of n square or big O of n square log n. See, over here it was equivalent to our gn. Over here this is our gn. So fn is equivalent to gn over here. And in these three scenarios, my fn is less than gn. So we say that for our fn, we can write all these notations. Now, all these are not wrong, but this one is asymptotically tight, which means tight over here means that it is very close to my actual answer. And these are asymptotically loose, which means that they are right but they are not very close to my actual answer. Now let's talk about omega. Omega is very much similar to big O, rather it is just opposite. See, over here we had less than equal to. here we have greater than equal to, which means that my function is either equal to, which is at this point, or it is greater than my c dot gn. So over here, when we have this greater than equal to equation, so we use our omega notation. Now over here, suppose we have fn is equals to n square. So now we know that as it has equal to, we can use this. So over here, gn is equivalent to fn. Now my fn can be greater than gn. So over here we can use n log n and log n, because these three are less than our fn. So we can say that these three are correct, but they are asymptotically loose, and this is asymptotically tight, which means that this is more close to my actual answer and these are not that close. So suppose we know that bubble sort works in order of n. So it will, we can clearly write it as order of n cube as well. This is not wrong, but this is not asymptotically tight. We can even write that our bubble sort works in omega of 1. This is not a wrong answer, but this means that it is not very, but this over here is not very close to my actual answer, whereas n square is the closest of my actual answer. Now another thing that you should notice is Bigo simply tells us that your algorithm will at max take this amount of time, which means that if I'm writing n square or n square log n, so this shows that my algorithm will take at max this amount of time, which means if I am given this much time, so my algorithm will surely complete its task within this time. Now omega tells that my algorithm takes at least this much amount of time, which means that if I write it as n log n, so it says that my algorithm will need at least n log n amount of time in order to complete the particular task. We can say it for others as well and for n square as well, because my see the actual answer is n square, so it will need at least n square amount of time in order to complete the task, and hence also these can be also written as the same. Now coming to our theta notation. Now let's see what is theta notation. Now see over here in this part, we can see that my function is greater than or equal to c1 dot gn because of this c1. Because when I convert this c1 into c2, it becomes greater than or equal to function, which is our fn. So when we know that in asymptotic notations, we just simply ignore these constants. So once these constants are ignored, we can tell easily that my function is equivalent to gn. For example, if my function was, if fn was 3n square, okay, and my gn was n square. Now, if I put the value of c2 as 4, so 4n square is greater than gn, c2 dot gn. If I put it as 3, so it becomes equal to. Now, on the other hand, if I put c1 as 1, so I will have n square, which is less than our 3n square. And if I put c1 as 3, so it becomes equal to. Now clearly when we just ignore these constants, so we have n square for both fn and gn, and hence we can say that it is of theta of n. Over here we'll have theta. For the same gn, if I can write fn is equals to big O of gn, and also for the same gn we can write it is equivalent to omega of gn. This means that my function is equal to theta of gn. See, this is the reason that for fn is equals to n square, we can only have fn is equals to theta of n square. Now coming to little o. Now little o and little omega are just a little just like big O and omega, but with a little difference. Over here we had an equal to sign, but over here we do not have the equal to sign, which means similarly for this, which means that the little o and little omega are either strictly greater or strictly less than. See, over here in Fn and for C dot Gn. Here we were taking it from the point it was becoming equal to, and then for the rest of the graph it is greater. But over here we take it from the point this C dot Gn strictly becomes greater than f of n. We do not take this point where it is equal to. Hence for n square, we cannot write it as n square, f of n is equals to small o or little o of n square. But we need values which are greater than n square, which are strictly greater than n square. And similarly for little omega, we didn't take it from the point it was becoming equal to, but we took it from the point from where it was strictly less than. So for n square, we cannot write that it is of small or little omega of n square. This cannot be written, but we can write it as little omega of n log n or 1. Now when we were talking about the quicksort algorithm, so we saw that our tree was coming of a shape like this. Now we can say that this is the level at this is the maximum level to which our tree can go, and this is the level which tells that at least these many levels are being traversed. Now if I am to calculate the time complexity for this, so what we do? We calculate the number of nodes and the time taken by each node. Now for this exactly for this tree, it is very difficult to find the correct number of nodes. So what we can do is, suppose I take this last level and I assume my whole tree to be complete. So now I can find the number of nodes, and then we know that every time my function is working for how much time, and then we can just simply calculate it. Or the other way can be that I just take this, that these many levels are always traversed no matter what, and then we calculate the time for this. Now suppose if the actual one was f of n. So now when we are taking this red one, so we can say that f of n is equals to order of Gn. And over here we can say it to be small o, because it is strictly greater, because this part is extra. And when we are talking about this part, which is the yellow one, we can say that f of n is equals to small omega or little omega of g of n, because this part is strictly less than our fn. We can also call it as big O. There is no problem with it, and this can be also called as our omega, because the big O has all the possibilities when it is when our Gn is greater, and also over here it is strictly less than is covered by our omega. So now let's see the case when we write it as theta. Now in merge sort, we saw that my tree was coming as a complete tree. So in this scenario, now if this is Fn, we can write it as order of Gn as well as omega of Gn, because we can calculate the total number of nodes over here, and hence when we can write it as both as big O and omega, so we can write it as theta of Gn. So this was all for today's video. Thank you.